it's 10:10.
Yes, sir.
All right, so we'll start our class. Okay, and would you please turn to the page of 396 of our textbook, okay? And I think last week uh, we finished talking about the random walk, okay? And we say that if a variable has a unit root, okay? Let me share my screen, okay? Okay, we say that if a variable has a unit root, then the equation 12.23 holds. In other words, the variable follows a random walk and is a non-stationary. Means the gamma equal to 1. All right. So, and we also talk about that to ensure that the equation we estimate are not spurious. It is important to find out if this time series is stationary. And we know that the random walk is a non-stationary. In other words, the relation between the random walk, the variable has a unit roots, is non-stationary. Okay, and there are basically three ways to examine the stationarity of a time series. And we will they are graphical analysis or parallelograms, and also the unit roots analysis. And I think we'll focus on the last one. I mean, the unit roots analysis, all right? But if I take some examples, I will also show the graphical analysis and parallelograms. Okay. All right. And let's see one of the examples shows in our textbook on page 397. It shows that there's an example which y variables is in dollars of a gallon of gas in Portland, in the United States, Oregon. Okay, and tuition is also in dollars for a semester of study at one of the college called Occidental College in Los Angeles. So the price here and the X tuition, you know, if we're thinking of this kind of regression, there's no relationship between the price of a gallon of gas in Portland and a tuition of at one college in Los Angeles. But if we look at the data, okay, here we just only have 10 observations, and the relationship shows adjusted R square is 94%, and the T statistics for the estimate of the tuition is 11.4, which is high and also significant. However, this kind of relationship is really nonsense. So we say this is called spurious regression. And in order to test whether this regression is spurious or not, we need to actually test for the stationarity of each variables. I mean, including y variables or x variables. Okay, and since the unit roots is test on one variable. Okay, so I will start at one of the example. I already give you the data last night, which is the example of EX. Okay, but before I doing that, let me sort of explain a little bit about the unit root test. Okay, let's see. Let's see what is the unit root test. Okay, basically we're using is what we call the Dickey-Fuller test. Okay, so let's see. To ensure the equation is not spurious, we need to test for the non-stationarity. Okay, first, visual examine the data or a diagram of data. This is what I call is the graphical analysis. And the second one, actually, if you read another other textbook, there's another way called parallelograms. Okay, I will show a little bit when I do the examples. And the third one is what we call now the Dickey-Fuller test. And we also say the Dickey-Fuller test is a unit root analysis because the Dickey-Fuller test examining the null hypothesis that the variable in question has a unit roots. Okay, let's see. If you want to understand the Dickey-Fuller test, okay, let's start with the equation 12.22, the relationship between yt and yt minus 1. There's a coefficient called alpha, okay? And by definition, we just know that if the absolute value of the gamma less than 1, then y is called stationary. Otherwise, it's non-stationary, okay? All right, so let's see. If we subtract yt minus 1 from both sides of the equation 12.22, so this one minus yt minus 1 on the left-hand side, also minus yt minus 1 on the right-hand side, and it becomes to 12.26. Okay? All right. Okay? And if we define the delta y, okay, usually we call this is the first difference. Okay, we define delta y is yt minus 1, and beta 1 is gamma minus 1. Okay, in other words, excuse me. Sorry, let me see how to back it. Okay. Okay, we define this one is delta y, and this one is beta. Okay, so just like this. So it becomes 12.27. So if the null hypothesis now is if yt contains unit roots, and alternative is y is stationary. So when we say null hypothesis yt contains unit roots, means this beta 1 is 0. In other words, when beta 1 is 0, gamma is equal to 1, which is what we call the random walk. Okay, so null hypothesis beta 1 equal to 0. An alternative will be beta 1 less than 0. Less than 0 means the gamma is between is less than 0 means gamma is between 0. Let me going back to gamma, absolute value of gamma 1 less 1, then y is stationary. Okay? So beta 1 is less than 0. Okay? So if we test the version of 12.27 about the coefficient of beta 1, and we can test whether the variable y is stationary or not. Okay, and usually we have 3 versions of Dickey-Fuller test. Okay, the equation 12.27. Okay, if you, this is also listed in our textbook. Okay, is from page 398 and 399. Okay, and the first version is what we just mentioned it, and usually we do have constant terms in an equation. Therefore, if we add constant terms beta 0, it becomes to 12.28. This is the second version. And if those variables is trend, okay, is trend up or trend down, then we will add another trend terms, which is t. Okay, then this is 12.29. Okay, and this usually we use these 3 versions. Okay, when we get to the e-views, then I will show you where to pick up either one of the version. All right, and the t here is, since this is a trend terms, so it means if we have the data, the t will becomes from the 1 up to the n observations. Okay, all right, and so in other words, with these 3 versions, we can test whether this variable is stationary or not. And let me explain a little bit about these 3 versions. Okay, and usually, since we have this trend, okay, so if we have the variables yt is really growing, okay, they trend up or trend down, okay, then we can choose 12.29 version. Okay, if the variable is not growing, for example, not growing very fast. Okay, so like interest rate. Okay, and usually like GDP or consumptions are very good examples that usually growing over times. So you will use 12.29 version. And for those like interest rate and employment rates, okay, they are pretty good examples of variables that are not growing. So you're going to use 12.28. Okay, all right. Usually 12.28 and 12.29 are most popular versions for Dickey-Fuller test. Okay, and by the way, if we are using Dickey-Fuller test, like we just say, uh, like we just say that we are going to do the test of this, okay? And Dickey-Fuller test is very like t-test, but they are not using the t-tables, okay? And their critical values are somewhat different from standard t-table. And it also depends on which versions you're using. Means that different version has different critical values, okay? And usually, if we are using eViews, the eViews will show us all critical values, okay? We don't have any separate tables you can refer to, okay? So just look at the eViews packages or Grados. They will provide these critical values with the output from the Dickey-Fuller test. Okay, and I also like to mention that which it didn't really show in our textbook, okay, but it is also, usually we do that way, okay, and this is what we when we say this is three version of Dickey-Fuller test. This is arrow terms, okay. Arrow terms, it follow. There's no zero correlations, okay. The assumption of this arrow terms is follow classical terms, means this is normal distribution, okay, without zero correlation. But since this is a time series data, the arrow terms usually have zero correlated. So this three version of Dickey-Fuller test has to modify it to take this zero correlation into account. And this adjustments is called augmented Dickey-Fuller test, which means this, okay? You see the difference between these three versions. I use the prime, okay, instead of another numbers of equation. I like all of you to do the comparison between Dickey-Fuller test and augmented Dickey-Fuller test. Okay, the difference is we add a series of lagged value of delta y to the regular Dickey-Fuller test. Okay, the regular Dickey-Fuller test is up to these parts without the last terms. Okay, we use this one to take a zero correlation into accounts. Okay, then I will also show you that where do we add all these terms when we use the eViews, okay, and also we use the Grados, okay, and let me come back here. This is what I also mentioned, that the Dickey-Fuller test, this is not the standard t-tables. I mean, the critical value is not standard t-tables, okay? And it will depends on the different version of the test. So, for example, this is if we have the sample size, and for 5% one-sided critical values, if you're using 12.28 version or 12.29, the critical value is really different. Okay? All right. And since we need to do the hypothesis testing, so I think it's better to use the examples. Okay, all right, so I'll stop the discussion of Dickey-Fuller test, and let's go on using the data EX, ln EX, to do the Dickey-Fuller test. Okay, let me get out of here. Okay, then all right. Okay, I already imported this EX and ln EX data into the Gradle. Okay, so I also, like all of you, maybe you can also try to import it into the eViews, and you also can do the practice. Okay, and so now we consider this economic time series, which is the exchange rate between US dollars and the euros. So the definition, okay, let me show this one. The definition of the variable EX, okay, is defined as dollars per unit of euros. So this is the exchange rates, and this is also daily data from January the 4th, 2000 to May 8th, 2008. So we have total 2,355 data. Okay, all right. And since this is the exchange rate, and we know that if we take the natural log of the daily dollar-euro exchange rate, then it becomes to natural log of EX. So let me show this data to all of you. So this is the original exchange rate, and this is the natural log of exchange rate. And the idea behind this natural log of exchange rate instead of the exchange rate itself is that the change in the natural log of variable represent a relative change, means rate of return. Okay, so we like to know the rate of return. So the difference, so like this one, if I use in, this is the first day, this is the second day, okay? So the rate of return from the first day to the second day, okay, you can just immediately using the log of EX minus. So you can use 0.162119 minus 0.1616531. This is the rate of return. Okay, but this is pretty similar when you using when we say the rate of return means if you are using EX, it means using 1.7060 minus 1.1812 divided by 1.1812. This is what we call rate of return. Okay, and it's easier if you take the natural log of the EX and you just take the difference between these two values, and the number is pretty similar. Okay, this is the idea. We're using natural log of the exchange rate. Okay, so if now, so from now on, I'm going to use the variable natural log of EX. Okay, first, we say that there are three ways to, to, to test the stationarity of the variable. The first one is the graphical analysis. And usually the graphical analysis is the intuitive way and also the intuitive feeling. Okay, so let's see. And let's see how do we see the graphicals. Okay, so I will open it, then using the view and the graph. Okay, and I hit OK. So what do you see from this graphical, this graph of LNEX? What did you see? How did you feel? It looks like it's trend down a little bit, then trend up. Okay, so usually this is not what we call stationary. This is not stationary. This is non-stationary. Okay, all right. And we also mentioned that the second way is look at the parallelogram. Okay, how do we, this two ways, it really didn't show in our textbook, but since this is very popular ways to do it, so I will also, since we're using eViews to do it, so I'll show you how to do it, okay? Then how do we see the parallelograms? Let me see. I can use also these functions. Did you see the function here is parallelogram? Okay, this is a function called parallelogram. So I hit this parallelograms and I'm looking at the levels, okay? And what lags including? Usually, if we look at parallelograms, we can take 1/3 or 1/4 of the data. However, we have this so many data. We don't have to see so many lags. We can see just up 30 or 36. Okay, so I'm going to just look at the first 36 lags. Then I hit the OK. And this is what we see, the parallelograms of LNEX. So how do we read these parallelograms? First of all, you can see this, what we call autocorrelation functions. This is called autocorrelation functions. It shows the partial correlation between those legs. Okay, then since it is correlation, let's see. Okay, since it is a correlation, and this correlation should be between +1 to -1. Okay, and look at the correlation of this autocorrelation here. The first one is 0.998. Then up to 36 is about 0.94. And this number is so high. Okay, this means there's the correlation between the current LNEX and the lag of the 1 day is really high. All right. Okay. In other words, if we see this one, we know that this variables ln ex is not stationary. Okay, so this is the second way, and I think our focus is on the Dickey-Fuller test. Okay, all right. So
Okay.
let me go back to
Excuse
me.
may I ask? You said before the number was very high, so it can be considered as they have correlation. I think is there have a standard or something like that?
Well, usually, let me see. Let me also open this one. Let me do this again, okay? All right. Usually, what is the non-correlation? If there's no correlation, what's the number of no correlation? It's close to zero, right?
Right.
Okay. If those autocorrelation coefficient is close to zero, means stationary. And this number is so close to 1, is very high. And it really it stays in these numbers up to 36 lags. The correlation coefficient is still 0.94. All right. So this is non-stationary.
Okay, understand. Thank you.
Okay. All right. Okay. So now we focus on no. Now we focus on the Dickey-Fuller test. So look at these functions. Also, the function view. There's another one called uniroot test. Okay. So here the uniroot test. Okay, I like to explain this parts. Okay. Look at this one. Test type. Okay. Usually this is called augmented Dickey-Fuller. Okay. And we just show you that the difference between Dickey-Fuller and augmented Dickey-Fuller. And we say that without the added terms. Okay, you all remember that Dickey-Fuller. Maybe can I show you the other one? Okay. The difference with this is the Dickey-Fuller test. The difference between Dickey-Fuller and augmented Dickey-Fuller is these terms, right? So these terms, okay? So if, let's go back to here. So if, look at this one, this parts, lag length. This is about augmented Dickey-Fuller test. Usually, there's some criterions. Okay, usually we're doing the first one, this archaic information criterion. Archaic information criterion. Okay, we know that the second one, Schwartz information criterion, is also popular, but never mind. There really no difference at all. You can try it. You can try and play with that. Okay, and if I show the lag length 0, if I show 0, means that I'm doing Dickey-Fuller test instead augmented Dickey-Fuller test. Okay, if I show 1, okay, then means that I have 1 lag of these parts. So this I equal to 1. You see what I mean? So these parts will tell us whether we're using augmented Dickey-Fuller test or Dickey-Fuller test. But usually, okay, we all call them augmented Dickey-Fuller test. If you take this 0, this augmented Dickey-Fuller test is what we call the Dickey-Fuller test. All right, and how many legs I'm going to use? Well, this is a very practical questions. Okay, then I'll explain it later on. Okay, and look at the left-hand parts. Okay, test for unit roots. Since these variables is level. Level means the original variables. First difference is taking the first difference. You mean taking the first difference of the original variables. Now I'm using the original variables, which is level. Okay, if you're doing the second difference means the difference of the first difference. Okay, and usually we started with the level. All right, then this part's include in test equation. There's a 3 options. One is intercept, means that I have the intercept. So means we have in the 12.28 version. Okay? If this is the second term trend and intercept. Trend and intercept means I'm using trend and the intercept. Okay, which is 12.29 version. Then none. None means no intercept, no trend. Okay, so this means the 27 version. All right. So now let's okay, let's look at, since this is the daily, let me go back. Okay, this is the daily data. Okay, and I think this is just a common sense. Usually for annual data, we may include 1 or 2 legs. So for the legs here, if you have annual data, you can try from the 1 or 2 first. Okay, if it is a quarterly data, okay, we started with the 4 legs. Okay, if it is a quarterly data, we start with 4. Then for the monthly data, we can start it with 12. Okay, then this is the daily data. Okay, I think daily data and monthly data is not that big difference. So I'm trying using 12 legs too. So this is 12, I'm using 12. Okay, and so I'll show from let's see. Okay, since this is exchange rate, and we just see the graph. Okay, we just see the graph. They do have a trend down first, then trend up. Means there's a trend, okay? And usually we're using intercept too. So I will choose in the trend and intercept. Okay, so first of all, I use the level because I'm using original LNTEX. And this is because when we look at the graph, it is really have trend. So I'm using trend, and usually we do intercept. So therefore I choose the middle one. Oh, so this is the version of 12.29. And the lag, since this is daily data, okay, I will try starting from 12. Okay, I can try more, but I'll try starting from 12, and I'm using archaic information criteria. Okay, then I'll hit OK. So I'm doing the unit root test, means I'm doing the Dickey-Fuller test. Okay, then I hit OK. All right, this is the output. Let's see. There's two parts, which is the upper one and the lower one. Let's see the lower one first. Okay, lower one is really the augmented Dickey-Fuller test. Did you remember the version of Dickey-Fuller test? I'm using 12.29. So what's the dependent variable? Is the first the difference of L and EX, right? I'll show this here to, can I show them both? I'm able to show them both. Maybe this one. Okay. All right. Can you see that clearly?
Yes, Prof.
Is it okay? Huh? Is it okay to see? It's clear?
Small Prof, I cannot see.
Yes, it is
Okay.
clear.
Okay, all right. So I'm using 12.29. So this version, right? So what's the Y variable? Is delta YT. So did you see that? The dependent variable is delta LNEX here. Okay, then I do have YT minus 1, so which is this terms. And C is the constant. And the trend is the T variable here. So I do have the regression output of 12.29. All right. So what we are interested in is the beta 1, right? Is the beta 1. So the coefficient of the beta 1 is negative 0.004088. And what's the T statistic? Is negative 3.2649. And the p-value is 0.0025. So remember that if we check the regular t-tables according to this result, this is the regular t-test probability p-values. But remember, this Dickey-Fuller test is different than according to the version of 12.29. Okay? The 1% level, the critical value is this number. 5% level, critical value is this numbers. 10% is this numbers, which is totally different from the t-tables. Okay, so according to all these critical values, the t statistic, this one, we're using the same t statistic. Okay, according to the Dickey-Fuller test, the critical values, this number is smaller than either one of them, right? So the probability, and we see the one-sided test, the probability is 0.1251. What do we mean by that? Do we reject the null hypothesis? Do we reject the null hypothesis? According to this probabilities, we do not reject the null hypothesis, right? So what is our hypothesis? Our hypothesis is this. It's this. So when beta 1 equal to 0 means what?
Is uniroot.
This is uniroot, so means non-stationary, right? So if we do not reject the null hypothesis, means what? Means we do have uniroots. You know, we have no enough evidence to show that they're stationary. This is the null hypothesis, non-stationary. An alternative hypothesis is stationary. So means according to the Dickey-Fuller test, and the probability shows that we cannot reject the null hypothesis. Therefore, the LNEX variables is non-stationary. Okay? Any questions?
Prof, can you repeat that? Sorry.
Pardon?
Can you
Excuse me?
repeat? Can you please repeat it? The analysis.
You consider what? Other version? Or different lags? Sure. Is this your
No,
question?
No, Prof. Just reject the null hypothesis.
I mean, first of all, you need to understand what's the null hypothesis here. Okay? The null hypothesis here is beta 1 equal to 0. Alternative is not equal to 0. So what do we mean by beta 1 equal to 0? So go back to this one. This part is delta y, and this part is beta 1, right? So when beta 1 equal to 0 means gamma equal to 1. And when gamma equal to 1 means random walk. And random walk is non-stationary. So Dickey-Fuller test is really a uniroot test. It is a uniroot test. Okay? Any questions? So this means that, okay, if I say, so null hypothesis is YT contains a uniroot, and alternative is YT is stationary. Means if null hypothesis holds, means uniroots, and means non-stationary. If the alternative hypothesis holds, means stationary. And according to the result, we just have it. This probability is greater than, either one of the levels. Okay, it's even greater than 10%. So we do not reject the null hypothesis. So we don't have enough evidence to show the LNEX is stationary. In other words, is non-stationary. Is that okay?
Yes, Prof.
So we're not comparing the t statistic.
No.
We just only see the probability.
Well, we using the t statistic. Look at this t statistic. But we're not comparing with the t table's critical value. This is from Dickey-Fuller test's critical value instead of t tables. If we look at t tables, the probability is this. It's reject the null hypothesis. But be careful, when we do the Dickey-Fuller test, this critical value is different from t tables. So the upper parts of this output, this already show you the probabilities, which is compared with the new critical values from Dickey-Fuller test. So this probability is different from this one. And Dickey-Fuller test, you need to see the probability here instead of this one.
Professor,
Okay?
Professor, I want to ask.
Okay, Prof.
All right. So let's stop here for a while. Then we'll come back. Let's come back to our. Okay, let's stop recording here for a while. Then we'll come back at the second meeting. Okay?
Okay, Prof.